Welcome back. Now it's time for Farbod to continue his series of lectures. Please. Yeah.
Thank you, everyone, for coming back. So today, I think I'm going to minimize the distance between my lectures and combinatorialists today. The global minimum will be today, but next lecture also will have some combinatorial stuff. So let me, since there was a break yesterday, thank you for that. Let me just remind you what kind of things have been happening. I'm going to put everything together tomorrow, but it would be good to not lose sight on where we are going. So I discussed heights, and then especially I focused on the notion of canonical heights for abelian varieties. Then on Tuesday, we talked a little bit about it should be decomposed into local contributions, and the hope is that the tropical geometry of Berkovich spaces have something to do with these local contributions. Then I started saying what Berkovich space is, especially for A1, which I want to start the day going from there. It was some kind of a tree. It is built from valuations. And I said in words, it's quite related to tropical geometry. I'll say more things. That's one of the main things I want to discuss today. And then, OK, so maybe today the plan is very quickly I'll say something about curves, analytified, also abelian varieties, analytified. For this, I spend a little bit more time because it's rather technical, but it's really beautiful theory. And it's a very useful theory. And then I focus on the notion of tropicalization. Maybe I quickly remind everyone one definition of tropicalization, which is closely related to what the working definition for Kris's lectures. And then, OK, this is a little bit going to take some time, but the rest are rather straightforward. My hope is today I also say something about curves and Jacobians in this context, and say something about how potential theory or capacity theory in the context of Berkovich spaces works very concretely in combinatorial terms. And along the way, I even mentioned chip firing and things like that. OK, before I start, any questions from previous lectures, any confusions that I might be able to help? Yes?
What happens if the evaluation is trivial?
So it's still a tree, but it's kind of an easier tree. Yeah, the infinite branching and things like that are much more manageable. Yeah. But I won't use that. My application for the entire lecture is completion of algebraic closure of QP, because I want to work with number fields. And so in my case, I don't want to spend time on it, but I'm happy to draw some pictures after the lecture. Any other questions? OK. Essentially, today's lecture is a bunch of examples, but some of them are theoretical, some of them are computational. The first one, I don't want to spend too much time. I just rely on something I said orally last time. In the theory of Riemann surfaces, when you want to say how they look like, you say they look like locally like a piece of complex plane. And now complex plane is replaced by a tree. So if you want to just formally say what a Berkovich curve should look like, well, they should locally look like a tree, which means globally, so curves. Let me just say nice curves. So you have to be a little bit, maybe let's say nice means smooth projective curves. It will be some type of object that has some global topology, but locally looks like a tree. OK, I can't draw a convincing picture, but it's some schematic of what's happening. It's that crazy tree, and then the points, the classical points, K points are there. The, There is some kind of a graph, global graph sitting right there. And then the points, the classical points, k points are there. There is some kind of a graph, global graph sitting right there. And then the points, the classical points, k points are there. There is some kind of a graph, global graph sitting right there. And then the points, the classical points, k points are there. There is some kind of a graph, global graph sitting right there. It's one-dimensional object, and then you have because trees are sort of uniquely geodesic, you also can bring, if you have a point, you can bring it down and put it on your graph. So this process, you might want to call it informally, at least for now, tropicalization. So one definition of tropical geometry could be study of the skeletons, which is this sort of polyhedral complex that sits inside the Berkovich space. Okay, I don't say too much about this, but you see graph theory sitting inside algebraic geometry. And there is a link, there is a function that takes algebraic geometry or arithmetic geometry to combinatorics. The next example, I'm going to give more details. So I guess this is example 2. Example 1 was this, which I did give a little bit more details. And I'm relying on that. Example 3 is going to be a abelian variety, and it's one of the most useful examples, certainly in my research, but it also classically over C. This is a beautiful story that you might or might not know, but very quickly, if you have A over C, the analytic version of that, the same way that a curve over C can be thought of as a Riemann surface. So this just means the C points, but together with the topology coming from C. This is isomorphic to a complex torus, meaning a complex vector space, G-dimensional vector space. G is the dimension of A. Modulo a lattice. And this theory, I mean, for elliptic curves, you probably have definitely, well, if you have seen elliptic curves, you have seen C mod lambda. In higher dimensions, this is a theory that certainly Riemann studied among others. And he even said, he asked the beautiful question that if I give you a complex torus, when is it that it's actually coming from an abelian variety? When is it algebraic? It's defined with algebraic equations. And there is a beautiful linear algebraic answer to that. Yes? It's the same, so it's compatible. Berkovich's theory applies to complex setup as well, but you don't have to believe me. Just think about classical complex geometry. Because the way that I defined Berkovich space, I assumed it's non-Archimedean. Yes?
If A is a curve, an elliptic curve, just so there's locally a tree, now you're saying it's just a circle.
This is over C. So if you want over non-Archimedean field, it will be just a circle or a point. So whether you get a genus 1 circle or not depends on, actually there is a theory around this by Tate. If it's a Tate curve, meaning the J invariant has some valuation which is, well, the uniformizing parameter should have absolute value less than 1, whatever that means for J invariant. Then you get a circle. If not, you get a point. If you didn't follow what I said, don't worry about it. In fact, I'm going to give a more general version of this in dimension 1 right now. Other question? Yes?
So you were saying that every curve is locally A1.
Yes?
So in the case of curves, you have this high covering.
Yeah.
Do you have a notion of Berkovich?
Yeah, it actually came up in, who talked about harmonic morphisms? Juicy talked about harmonic morphisms, and there was a question about this dilated maps. So the question of what étale maps translate to on the level of skeleton is precisely the harmonic morphisms in that language. This is also well studied by, help me, Amini, Brugler, Baker, Rabinoff. There are 2 papers on this. Did I make a mistake? Can anyone verify it's on video? Should I correct the name of authors? Okay. Okay, so complex abelian varieties have this beautiful theory, which is highly transcendental, by the way. You cannot have this kind of uniformization. So this is universal cover modulo fundamental group. You cannot have this uniformization in algebraic category. This map is highly transcendental, the quotient map. So there is no hope of having something like this or such a beautiful theory in the algebraic category. But now we have an analytic space. And in fact, essentially for free, I can say over a non-Archimedean field, I must have, this is a topological space. I do have a universal cover, honest to God universal cover, and a fundamental group, which is going, my notation is going to make some toric people very upset. I'll say why. So this is the universal cover. This map is highly transcendental. It makes sense in Berkovich's category, but not in algebraic category. And there is a let's say, fundamental group describing the deck transformation, where Y is the fundamental group, pi 1 of AN. Well, I should say base point, but just like in the classical setting, this is actually abelian. So the base point doesn't matter. It's up to conjugation. Nothing happens with conjugation. And you can think of this, because it's abelian, it's the same as the first homology. It turns out this is a discrete lattice. I'm going to say what lattice this is. But so Raynaud, so-called Raynaud's uniformization or Raynaud cross, describes what this, the possibility for E is. Namely, in the algebraic category, E can be uniformized, can be thought of as a semi-abelian variety. Where this is algebraic torus, which is mentioned in a couple of different contexts. It's certainly important for tropicalization, but also in toric lectures, this is what you compactify. So this is algebraic torus. You should think of it as spec of K bracket something. And again, apologize, I'm not going to use M or N. And unfortunately, I've used X, but this is in the book of Faltings and Chai, X and Y are replacing M and N. So sorry, but there's a good reason for that. So abelian varieties have duality, and you want M and N to switch with the dual abelian variety. So it would be even more confusing if you wanted to be faithful to M and N terminology. Then M of something would be N of the other one, and so on. So X is actually a lattice, which so this is X is I think I should say characters of the torus, and Y is co-characters. Because of the important duality in here, I'm going to always have this dual object in mind. Okay, so this the Raynaud's result is saying that the universal cover is an identification of some semi-abelian varieties. And if it bothers you, so this is another abelian variety, by the way, which has further the property that it has good reduction. You're working over an Archimedean field, it makes sense to say, quote unquote, good reduction. I don't want to dwell on these technical points, but it will be helpful because there will be a tropicalization map from T, the usual tropicalization map, very soon. And it turns out because this B is not a knowing, you can extend it to E. So you will have a tropicalization map here. And then you descend it here. I'm going to say these things, but just this good reduction condition is helpful. But if it bothers you, actually, it's perfectly fine, and it happens for good reasons that sometimes this B is 0. So your universal cover is actually just an identification of the algebraic torus. So you should think of this. So if B is 0, which is OK sometimes, think AN is like K star to the power of G, well, an identification of that, modulo a lattice. And this is closely related to C to the G modular lattice. If you apply exponential to this, you get exactly that. So in the case that B is 0, more or less you have the classical theory after you apply exponential map. And that exponential map is important because in an Archimedean setup, you cannot have an additive lattice. You have to go to multiplicative side. And that's an observation by Tate, by the way, before Berkovich spaces. Anyway, so these are some technical, don't get too bogged down on the technical things I'm saying, just you can uniformize abelian variety, and the universal cover is more or less algebraic, identification of algebraic torus, modulo some subtlety that can happen.
For this result, you are assuming that A has semi-stable reduction?
I am working,
That's right, otherwise it should be.
yes, because I actually, this is split already. Let me, I'm going to apply everything over CP eventually, which is QP. So in this case, everything is true. I'm not going to give the most general statements, but you're absolutely correct that I have to make sure semi-abelian reduction is happening. Over a large enough field, this happens. Okay, so what is tropicalization? Let me go back. I want to describe how this picture for abelian varieties. Let me go back for a second and talk about tropicalization as you learn in your kindergarten. Yes?
In the one-dimensional case, can you draw how this lambda lattice sits inside the tree?
Yes. Yes, but I don't do it right now. I'll draw the one or n-dimensional picture in a moment. But so there is this line GM, which is, so this tree, I said I won't draw, but so there is this line from 0 to infinity. There is a periodic lattice sitting on it, which when you mod out, you get a picture like this. So I won't repeat that, but I'm happy to chat afterwards. So recall, tropicalization is a process that takes logarithm of absolute values. Yes? B is canonically attached to A, but it's not, I mean, there exists a B. That's it. So there exists a universal cover where the universal cover is a semi-abelian variety, which is an extension of this good reduction B and a T.
Okay, so this was kind of an explanation where the E comes.
Yes. Yes. And in nice cases, when bad things don't happen, B is 0. I mean, if in maximally degenerate case, B is 0. And I would like you to be comfortable with that. That's a very good class of, if you have, for example, Mumford curve, its Jacobian will have this property. Or in the case of Tate curve, this also, again, is 0.
Can I ask another question?
Of course.
You wrote down upstairs why is the Tom to be group, and downstairs why is the Tom of something that I can't read?
T dual, the dual torus. These are part of the theorem. So there is the same phenomenon happening for the dual lattice. This is something you don't care about over complex numbers, but for the dual abelian variety, there is a similar prime and prime, and it turns out y of that is x of this is y of that, and then there are maps that relate the two different abelian varieties, and those compatibilities I'm kind of summarizing in the minimal way possible that I need. But there are really, I have to draw two Raynaud short exact sequences.
But this means there's an isomorphism. The upper y is the same as the lower y.
Say it again. This y is the same y, yes. I haven't made a mistake. These are the, so I'm saying the fundamental group can be described as the Hom of the dual torus to GM. Thank you. Any other confusion, questions? Yes, but trust me, it's good to be careful. There is also dual of this, and in the principal polarized case, they are all isomorphic, and then some people just identify them, and it's really annoying. So I want to just, there exists isomorphism between various things that I write down, but let me not do that. Okay, so back to tropicalization. You have this map in coordinates. What do? You go to algebraic torus because you like the fact that nothing is 0. And then you have a tuple, maybe Z1 up to ZG. You send it to, since I'm already over in an Archimedean field, I can just take the valuation, which is logarithm of absolute value of Z1 all the way to valuation of ZG. So in Kris's introduction, there was first a T, and T goes to 0. You can reinterpret that as doing things over formal power series or Poisson series, and it's the same process when you send T to 0.
It's R to the N.
R to the G. Yes, thank you. This is what you do in coordinates. And then if you have something X here, you apply this map. So by composition, the inclusion with this, you get some kind of a polyhedral object. And it's often actually annoying that maybe if you start with a X in here, you'll get something that has actually, this didn't come up because with amoebas you don't get this annoying situations, but it can be that it almost looks like a tropical line, but then you have to closure the image to actually get a line. It's a bunch of dots that look like a line. So maybe trop of X, you might, I've used X. I'm not allowed to use it. B used. M is bad. A, B, C, D, E. Give me a variety which is not. Oh, curly X. Yeah, it was used. Thank you. Is the closure of the image. Let's call this trop map. That's a repetition, but it's not too bad. Closure of the image. Of this. Okay. And this closure is annoying. And one observation by Gubler was that you can actually analytify the situation and this closure goes away. But it's not just for cuteness that closure goes away. It's very helpful because then you can apply tropicalization to Berkovich spaces. So tropicalization, the motto is tropicalization factors through analytification. And that's actually quite nice. And I can write it down without choosing coordinates. So if you have, let's say, this inclusion, let's call it, it doesn't really have to be inclusion. It can be a rational map, but OK, let me not be too concerned. Analytification is a functorial process. You can actually take this morphism and analytify. And it turns out you have a tropicalization map. Here, according to my choice of X, this is bad. Now I don't like this X. It's my attempt to write a MathCal or whatever script. Why? So this is the kind of thing that I wanted to avoid earlier. So I want dual of X. So you think of this as what? Hom of X R. And this is ultimately, if that's a lattice of dimension G, this is like R to the G. But I want to do coordinate free. And it's actually quite, if you think about it, it's quite natural. Remember, points in Berkovich space are some kind of semi-norms. It's some kind of a machine that you feed in a function, you get a real number, right? Now, I have a point, which is this machine, and I want to, given a character, produce a real number, right? Well, feed the character to your machine, get a number. So it might look like I'm doing something genius, but that's the only thing you can do. This is my character. I produce a real number, which is apply the character to that. And since I want things to be additive, not multiplicative, I put a log. And I must admit whether I should put a negative here or negative here or positive is a controversy that people should make a choice once in their lives and stick with it. And I'm not willing to do that because I'll mess up. Okay, I'll put a negative because my note says negative, but I might not be faithful to that. Okay, so this is recall. So the first part is recall from tropical geometry. The second part is how to upgrade it to Berkovich spaces with essentially no effort. The moment you know the definition of Berkovich space, you get a tropicalization map from T. Okay? Which means I have a tropicalization map here for this T and its analytification. The fact that this B is super nice, it naturally extends. It's a little bit technical to write down, but this tropicalization map naturally extends here. In a way, the contribution from B to the elements in the middle happen in the kernel of tropicalization. They die as you tropicalize. Okay? Making this sentence precise is technical, but so you get a, so back to the previous board, back to AN, this also induces a trop map from E analytification to real numbers or X R star. Okay? I told you how it works on the T part of it, and I'm saying the B part goes to 0. Okay? And I've been encouraging you to think of B as being 0, which means that you're good to go. You already know T. Okay. Now I can say how, according to all this theory, how an abelian variety should look like in Berkovich's category. Namely, you have this uniformization sequence. You apply trop here because I said it exists. And you get this X star R. You get a map to a real vector space. This is. Then by restriction, you can also apply trop here. It turns out you get precisely Y. So you apply to this subset, trop as a sublattice, some discrete subset. You apply this, and you get precisely Y as a subset of the dual. So I'm going to actually, for the convenience, I'm just going to write this as equality. And then this is completed by some sigma. And you get an induced projection, which also by, I should probably put a hat here, just so that I don't have too many trops, but with abuse of notation, I call this tropicalization map. So now let me draw a picture. What's happening? So this thing is a real torus. Whose dimension is very much like the dimension of the T, because in the case that B is 0, the dimension of T is the same as dimension of your abelian variety, and it's going to be G-dimensional. But it can be that this real torus has lost dimension. You start with the G-dimensional thing. It will distribute between B and T. If B picks up some dimension, it's not 0, then T is smaller, therefore X is smaller, and therefore your torus is smaller. So I essentially, this describes the picture that you should have in mind. This is going to be my skeleton, which is a real torus. And I said all Berkovich spaces have some kind of a polyhedral complex sitting inside them. And then you have these original number theoretic points, your k points. And then there are these hairy stuff, just like the curve case. There are these hairy stuff, except the hairs might be more than dimension 1. There might be like weird hairs. But they're, so this is a deformation retraction. And not only, more or less, I have hopefully convinced you that there is such a picture, but I've also told you that there is a canonical way to retract points to the skeleton. So there is a canonical skeleton, and then also there is, okay, if it was one-dimensional hair, it's already, there's only one choice, but in these situations, I'm also telling you that there is a concrete way to come to the skeleton. And this coming down to skeleton, how you can come down is an important question. In abelian varieties, we get lucky. In curves, there's no choice. You don't even need a luck. But then if you ask the same questions over more complicated things, then you have very interesting questions to answer. So this is actually a dimension 1 version of that. Dimension here is some g prime, which I have made some bad choices already. I've been calling it g. So let me not write it down. This dimension can be smaller, potentially can be smaller than the dimension of the original A. In good case that B is 0, or in lucky case that B is 0, dimension doesn't drop. You start with a g-dimensional vectors abelian variety, you get a g-dimensional real torus.
Can it be 0?
It can be 0. In fact, Tate, for a while, was confused that why he can only, in his rigid analytic setup, he can only uniformize certain type of varieties. It turns out the condition was precisely because B, if in dimension 1, so you have only 1. So it's either 1 plus 0 or 0 plus 1. So in non-Tate curve situation, this is 0. The universal cover is just itself. So there's no uniformization for non-Tate elliptic curves. Yes?
Why sigma lies inside the definition of A?
Why sigma lies? So that's a good question that I haven't justified, and I don't want to justify now, but it lies in there. Yeah.
So is the analytification of an abelian variety a group?
No. The skeleton is a group.
Okay.
There is no group structure. If you give me 2 points here,
So
there's an entire chapter in Berkovich's book. If you analytify a group, what do you get? It turns out you can call it analytic group, but it doesn't have a group law. It has some star product or something.
okay, so that's not a short exact sequence up there.
Up where? Here?
Yeah, the 0 to y to e.
Not in the, it's in the topological category, not in the group. Not in the sense of groups. I'm saying universal cover and fundamental group. You can do that for any top. Yeah. Yeah.
What was the difference between thick lines and orange lines?
I was just saying that I don't want to insist, I don't want to draw my picture and give you the wrong impression that the retraction map is via taking lines. It can be some contractible pieces that are like 10-dimensional. So it's pretty amazing that you have a canonical path to go to the skeleton, which is not a given thing. If it's not abelian varieties and you don't have Reynolds uniformization, this is a very mysterious question. Is there the best way to go to the skeleton? And it's a question of importance, not just curiosity. Yes?
How does this compare to skeleton case we have a strictly semi-stable model?
So I mentioned it last time orally, but let me repeat. If you have a nice model, semi-stable model, or even, I think, KLT model, I don't remember the exact terminology. You have a dual complex. That dual complex has an embedding inside the Berkovich space. So the thing you're discussing has an embedding here. The same way for the graph situation. If you have a dual graph, it has an embedding here. And you can even think of this in a precise way as limit of all possible models, all possible dual graphs. You should have, the limit will be a metric graph. And in that case, the limit will be the skeleton that I'm describing.
But does the skeleton always?
So I've described the canonical skeleton, but if you have models, you might have offshoots as well. There's a paper by Gubler, but it embeds inside Berkovich space, and all of them together are not going to violate this picture that I'm saying. So,
But can you realize this essential skeleton as
a limit of models, not necessarily as a single model. Yeah, it's actually quite related to Tate's trick. I mean, I'm not talking about the same situation at the same time. But in the Tate situation, you had this one function h hat d, which was not really coming from a line bundle, but it was coming from a limiting process. So if the same phenomenon is happening here, and it's actually not unrelated, you can make that precise, that this is a limit of models that gives you this kind of canonical skeletons. OK. I'm almost surely running behind time, but it's great to have engagement from the audience. 15 minutes according to my, 15 plus 10, I have some permission. So this was my second example. Maybe let me end by saying that so far I assume just abelian variety. What if you have a polarization on your abelian variety, which you can think of it in a variety of ways in the case of abelian varieties? Take your favorite way. It can be some map between abelian variety or its dual, and its dual, it can be some line bundle. But let's just be vague. Polarization is some extra data like line bundle. A polarization on A gives you a bilinear form on these lattices. So it gives you some bilinear form, which I use angle bracket on y times y. So we can think of it like a Riemannian metric on the skeleton. So I'm saying this real torus. If you give me a polarization, I can extract from that polarization some extra data that I can put on this torus. And in concrete cases, I'll describe what this bilinear form is. So, and if you have a bilinear form here, you can extend it here. So you can think of it like a bilinear form on the universal cover or the tangent space at the origin. That's why I called it a Riemannian metric. It's a group. You can move your tangent space anywhere you want. OK, I'll be concrete about the case of Jacobians. So in fact, that's what I wanted to do now. Example 4. It's actually relating example 2 and 3 and combinatorics and chip firing. So let's say X is a nice curve. Curves have Jacobians, which are abelian varieties. J is Jacobian of X. You can think of it as line bundles of first Chern class 0, or divisors of degree 0 modulo equivalence. OK, so the picture for Xn and the picture for Jn were described in the previous two examples. Here you have some kind of a graph and some hairy things attached to it. And here you have some kind of a torus and some things attached to it. In particular, so these are not maps, even though there exists a map, but just squiggly lines. This has a graph, metric graph. At least, in the running example, you can think of this compact part, or if you, it's okay if you want to take some of these lines as well, but let's say compact metric graph. And this one has a skeleton, which is the real torus. And then you can ask, is there a combinatorial machine that I just forget about the upstairs and just go from the graph to its torus? And the answer is yes. And it's chip firing, or even more explicitly using space of flows on graphs. So this is a very combinatorial thing. Sigma is so-called Jacobian of that metric graph, which can be described in two different ways. I love chip firing, but it's actually more informative to use flows. So claim. This in various generalities is a long history. The last paper is by Baker and Rabinoff from 2016-17. But the story starts from actually SGA. In the case of fixing a model, he already computed something related to this. He wasn't talking about Berkovich spaces, but Van der Put, in the case of B equal to 0, I think. And then eventually the modern exposition is by Baker and Rabinoff, which really uses the tropical language, which says sigma, the skeleton can be described concretely in terms of Jacobian of the graph, or Picard of the graph. And there's an isomorphism between them, which has been purely tropically described in the paper by Mikhalkin and Jarkov, and a combinatorial version of that was in Baker and Faber paper. So here, I mean, take divisors of degree 0 on the graph. It's modulo chip firing. And I realize nobody has actually defined chip firing, even though there were multiple talks on chip firing. So either I should get away with saying everybody knows, or I can't. So chip firing is, in just one word, if you have, so divisors are just formal combinations of points. And the idea is if you have some number of chips, you can pick all directions going out of that place and send your chips the same amount away. And be careful not hit a branch point. So stop at branch points and restart at branch points. So one chip firing move, which is actually generating the entire class, could be pick an epsilon away, which doesn't hit any bad branching points. Remove this and put $1 here, $1 here. And you can do the reverse process. You can borrow, you can fire. From this definition, it's not clear. It's not even clear that this is going to give you a real torus. But it does give you a real torus. This definition is my favorite in this context because it's much, much easier to work with, and it gives you more information. And it immediately shows that it's a G-dimensional thing. Namely, you can think of this as space of real flows. Real flows on gamma modulo integer flows on gamma. This is just another way of saying, okay. I don't want to write the, so these are first simplicial homology and with integer coefficients and with real coefficients. But homology and cohomology, you have to, again, be careful with isomorphisms because I don't want to commit to a sin. This is supposed to be a y, this is supposed to be x star, so I have to be careful about what is what. But anyway, what is a real flow? Some of your, so flow is some assignment of numbers to edges that has this sort of almost balancing condition. You can think of it like a balancing condition, but The concept of flow is much older. You just want, let's say maybe a water is going down at the rate 2 here, and then -1 here, -1 here. At any point, the same amount of water is coming into the pipe as it's going out of the pipe. No pipe is going to explode. And integer means that put integer numbers. Real means you're allowed to put real numbers. Right? And integer ones form a group. You can add 2 integer flows, get another integer flow. You have a 0 flow, so on and so forth. And real ones form a vector space. So you have a G-dimensional. OK, now G is the genus of the graph, which is rank of the fundamental group or dimension of the flow space. You have a G-dimensional vector space, and you have a G-dimensional subgroup in it. So you do get you mod out, you get a torus. So this is some kind of a, so at least it's clear from this definition you do have a torus, and the claim is that it's the torus that sits inside the Berkovich identification of the corresponding Jacobian.
The dimension of the torus is the genus of the graph, not the
Correct, correct. And that drop can also happen here. So if your Jacobian has a B, and it's going to be a drop, correspondingly, your curve also will have some points that have, I think, what's called, I would call them polarization. In the language of dual graph, you have irreducible components of higher genus. So you have some kind of a labeling on vertices here. I like polarization, but I'm sure it was called vertex weights. I try to avoid the word weight because I don't know which one is weight, which one is length, which one is what, genus. In arithmetic geometry, people call it polarized metric graph. So that's a common terminology. OK. Oh, yeah. Then the very last part, I said there is a bilinear form coming from polarization. Give me 1 second. Here, Jacobians are canonically principally polarized. They have a canonical line bundle on them, which is, you can think of the image of the Abel-Jacobi map, the G minus first image of the Abel-Jacobi map. It gives you a divisor, and you can look at that line bundle. There are various ways to say that a Jacobian is canonically principally polarized. So you have a polarization. So there should be a God-given bilinear form on the space of flows, which I will describe next. But Oliver?
Yeah. A little confused. I just know the chip firing definitions. But this is a discrete group, or I mean.
No, it's so divisors on graph. You probably have seen the original, the old, not old, yeah. One version of chip firing was on finite graphs. Now I'm working on metric graphs. That's why I picked these epsilons. I'm allowed to drop my chips anywhere on the graph. So divisors of degree 0 is like gamma to the.
So divisors are still integer values.
Divisors are integer valued, but they're allowed to be anywhere on the graph. In the finite graph situation, it's a finitely generated abelian group. Your generators of vertices. Now it's an infinitely generated abelian group, so it's a crazy group. That's why I said it's even not clear why the quotient is a finite dimensional torus. But there's a version of chip firing which is on finite graphs, and that's a finite group, and everything is actually sitting inside it. That's not unrelated to my theorem next time, but that finite group sits inside this infinite group. Other questions? So what I have to do next is to tell you what is this bilinear form. So if you give me 2 flows, how do you look at the product of them? That's what I want, right? It turns out the space of flows are generated by simple cycles. And for that, you can even fix a spanning tree and look at non-edges of the spanning tree. Basis of the dual matroid for this crowd. And that gives you a basis for the space of flows. So in very concrete terms, so let me say flow spaces are generated by, I'll call them simple cycles, but really circuits of the matroid. Simple cycles. Let me do it in a concrete example. The recipe is actually you pick a spanning tree. Well, one recipe is to pick a spanning tree like this one. So fix a model, put some vertices. Fix a spanning tree. For any non-edge of the spanning tree, you get a fundamental cycle. So if you add this, let me put an arrow. If you add this, you get this simple cycle, which also gives you a flow. Just think of water just circulating in this circle. 1 minus 1. And if you pick this non-edge of the spanning tree, you get another flow. And it's a basic fact that genus is the number of non-edges of a spanning tree. And it's a basic fact that these G cycles that I mentioned are going to generate the space of flows. And now I'm going to just say, after this bilinear form that should exist is cycle intersection pairing. And I suspect, now you all know what I mean by that. I have to tell you what happens to products of flows. Well, it's enough to say what happens to the generators. And generators are cycles. So if you give me 2 cycles, I can look at their intersection and record the length of the intersection. So like this comma this is going to be the length of this edge. Is that clear? Ish?
If you start with a spanning tree, all the length will be the same because it will be the length of the spanning tree.
No, this is too simple to make that kind of confusing. So if I pick this spanning tree, so this is G, this is my T, then one cycle will be this, if I add this, and the other cycle will be this. And the product of these two is going to be the length of this. My example was too small to confuse everyone. Okay. So I'm at 50-minute mark. Can I go more, or
Take 5 minutes.
5 minutes. Okay. So I'm done with the examples. This is all the spaces that I need to give you some formulas for heights. But in order to give formulas for heights, I want to do analysis on Berkovich spaces. Remember, the dream was to use Berkovich spaces, use analytic methods. And what is analysis on Berkovich spaces? I claim analysis on Berkovich spaces is, Berkovich curves is more or less electrical networks. So that's another very concrete part of the talk. So, and I'll say this very quickly. Maybe next time when I want to use it, I'll be a little bit more detailed. Potential theory on Berkovich curves, at least for my purposes, this is identical to electrical networks in the sense of Kirchhoff from 1853 paper. Why is that? Because, so I'll be brief and come back to it tomorrow. A fundamental problem in potential theory is to solve a Poisson equation. What does that mean? You have a Laplacian operator. It's distributional Laplacian. Distributional Laplacian. And I'm working on let's say, graphs, but Berkovich curves are some kind of graphs. This gives you a map from piecewise linear functions with integer slopes, piecewise linear or affine functions with integer slopes. Actually, I don't need integer slopes, with continuous piecewise linear functions for now. Sometimes you put extra condition on it. It's a real vector space. And then the output of this is supposed to be discrete measures of total mass 0. So let me tell you what this distribution Laplacian is in a very basic calculus example. So analysts for a long time have realized the second derivative is more important than the first derivative. First derivative can be skipped. If I have like y equal to absolute value of x, in calculus you can say what's the first derivative? Well, it's 1 and minus 1. The slopes are 1 and minus 1, but of course at 0 you don't have first derivative. But the second derivative is not that bad. It turns out there is a sense in which the second derivative is supposed to be a generalized function, or maybe in an abstract sense it should be a measure, and that's what I'm doing. So for the second derivative, you measure the jump here, which is 2, and you put a 2 delta here. Okay? So analysts skip this and say distribution Laplacian is the process that takes a piecewise linear function, or if it's continuous and it has second derivative, then you just do the second derivative. That's okay. But in these cases that things are not nice, you still can actually make sense of jumping using Dirichlet pairing, and you want the behavior of these second derivatives be nice when you are taking integrations. You want second derivative is very important under integration, and you can do measure theory. So next time using this distribution Laplacian, which I hope I don't have to explain too much, I'm going to do some basic electrical network theory. And then using that, I relate a bunch of invariants I compute in numbers from Berkovich curves and Berkovich Jacobians. And I show that these are actually computing local heights and even faulting heights and all sorts of things by doing this kind of high school physics stuff. So I'll stop here.